In a previous video, I showed the very important fact that the general solution to our basic differential equation, y prime equals ky, so the general solution to y prime equals ky is y of t is ce to the kt, which we've seen models the population of bacteria. And now let us elaborate on this a little bit. What does it mean for something to be a solution and also the general solution? This is what's called existence and uniqueness. So let's cover the existence part first. Okay. So let's show that y is ce to the kt solves the differential equation. Y prime equals ky. So this means existence. So there is a solution to this. Well, same as before, what do? We plug in ce to the kt on the left-hand side and on the right-hand side and see if it matches. So left, we had y prime, which is ce to the kt prime. And again, using the chain rule, this becomes ck e to the kt. It checks out. I guess it's ck e to the kt. On the other hand, for the right-hand side, let's do ky. I'd like to remind you, y is ce to the kt. So this will be ck times ce to the kt. And notice that's precisely the same thing as ck e to the kt. So you see, both sides match. So yes, ce to the kt solves this equation. Once again, that is called existence. I give you a formula, you plug it in, and you show that it solves the OD. On the other side, there is uniqueness, which is a bit trickier to understand. Namely, let's show that there are no other solutions to this differential equation. Because a priori, your friend could tell you a different solution to this with sines and cosines, but we want to show that this does not happen. Show that y is ce to the kt is the only solution. Y prime equals ky. So in other words, if your friend finds a solution to this equation, then that friend should also find ce to the kt. There are no other solutions to this. And this is a little bit trickier, a little bit proofier, but I will motivate this at the end. So suppose y is any solution to y prime equals ky. So in other words, suppose your friend finds a solution to y prime equals ky, and you need to show that y is in fact ce to the kt. And for this, consider the following, and again, I will motivate this at the end. You take y, you multiply by e to the minus kt, and you differentiate. Once again, very mysterious now. I will explain it. But now we can use the product rule. So this becomes y prime e to the minus kt plus y e to the minus kt prime. And that becomes y prime e to the minus kt plus y, and then chain rule, minus k e to the minus kt. But remember, y is not arbitrary. It solves the differential equation. So we know that y prime is in fact ky. So we get ky e to the minus kt, and then minus ky e to the minus kt. And this cancels out, and it turns out we get 0. And let's see how we can interpret this. So we know the derivative of y e to the minus kt is 0. Now remember, if f prime equals 0 always, so if a particle has 0 velocity, it never moves. So it's constant. So now y e to the minus kt is a constant, and we ultimately obtain that y is ce to the kt. And we are done. And let me explain once again why this was useful. So we wanted to show that ce to the kt is the only solution to this differential equation. What we did, we supposed y is any solution to this ODE, even the one that your friend got. And then we did some mysterious math, and then ultimately we obtained that y is ce to the kt. So the solution that your friend found is the same one as the solution that you found. And this is called uniqueness. There are no other solutions to this. There's no solution of the form sine of t or cosine of t. They're all of the form ce to the kt. And again, I want to emphasize, in this step, we never assumed that y is ce to the kt. We started with an arbitrary y, and we found ce to the kt. That's what uniqueness is. And just a little aside, of course, how did we obtain? We obtain y e to the minus kt prime. Well, here we cheated a little bit. And the thing is, with uniqueness, it really depends on the differential equation. If our solution were ce to the kt, then if you divide by e to the kt, then y e to the minus kt is a constant. And in particular, the derivative of this prime was c prime, which is 0. So if y had this form, then that derivative would be 0. And kind of what we did, we reversed this. We started with y e to the minus kt prime. We showed it 0. And then we found that y is ce to the kt. And on the homework, you will see a second order analog of this as well.